this question is an advanced question. Okay, this is rather in the graduate level, this one. And here it is related to the normal distribution. Okay, so this time we are going to calculate the expected value of a function of a normal random variable. And you know, the normal random variable is actually quite complicated to deal with in theory. In practice, we can calculate the respective probabilities related to normal random variable by using the CDF table of a standard normal random variable, but the theoretical calculations are a little tricky in normal distribution. Okay, so we are going to state that X here, capital X here, is a normal random variable with location parameter mu, which is also the expected value if you remember, and the scale parameter is sigma, which is also equal to the standard deviation of the distribution, and the variance is equal to the square of the sigma square. So if X is a normal random variable with mean mu, average mu, and standard deviation sigma, then the probability density function of that normal random variable was equal to 1 over sigma times square root of 2 pi e to the power minus x minus mu square over 2 sigma square. And remember now, we have the standard normal random variable where the location parameter or the expected value is equal to 0 and the scale parameter or the standard deviation is equal to 1. So a standard normal random variable is a normal random variable with expected value or average 0 and standard deviation or variance equal to 1. Okay, if the standard deviation is equal to 1, then the variance is also equal to 1 because square of 1 is 1. Now, in that case, the standard normal random variable has a PDF, which is denoted by phi of x, which is a little simpler than this form, because when you replace sigma as 1 and mu as 0, you get 1 over square root of 2 pi times e to the power minus x square over 2. Okay, so in the first part of this question, it asks, compute the expected value of e to the power z. E to the power z. Z is a standard normal random variable. So it says calculate the expected value of e to the power z, which is a function of a standard normal random variable. Okay. Now you may think that, so just for practical purposes, practicing purposes, just for giving the students a hard time, the question is asking such an expectation. Actually, no, my friends. This expectation is a very important expectation in theory. Okay, this is a very, very, very important expectation that we calculate in theory, but I'm not going to teach that. This is, as I have said, this is a little graduate level topic. Okay, I'm not going to explain why this expected value is important, but if you are interested in this, you can check the topics of moment generating functions first. So you can Google the moment generating functions, and you can also Google the log normal random variable to learn why expected value of e to the power z is important. Okay, now in any way, we are just going to calculate that expectation for practical purposes. Okay, now let's do that. Before reading part B, let's calculate the expected value of e to the power z. This is going to be calculated as the integral of e to the power x, which is my input function in the expected value, the function of the input random variable, times the PDF, which is phi x, and expands as 1 over square root of 2 pi times e to the power minus x square over 2. We are going to calculate that integral from minus infinity to plus infinity. Why? Because if you remember, a normal random variable can take any real value from minus infinity to plus infinity. So this is the integral that we are supposed to calculate for this question. Now, you see e to the power x, and we have e to the power minus x square over 2. Both of these exponential functions, obviously, they have the same base, which is the Euler number. Okay? So, because they have the same base, we are going to sum the powers up. The powers will be summed up, and we are going to rewrite this integrand as 1 over square root of 2 pi e to the power minus x squared minus 2x over 2, because when you sum up the powers, this is what you are going to get. Okay. Now I am going to do a trick again. Okay. So I like to do these tricks in order to solve such integrals. So in the numerator, in the power, in that power, we have numerator x squared minus 2x. Now I am going to add 1 and subtract 1 from that numerator. So let me make it a little closer for you. Okay. I am going to add plus 1 and minus 1 in the numerator, which is not going to change the solution at all, because if you add 1 and subtract 1 from any value, it doesn't affect that. Okay. But why I am doing this? Let me explain. Now, x squared minus 2x plus 1 is what? It's the square of x minus 1, right? X squared minus 2x plus 1 is the expansion of x minus 1 to the power 2. It's the binomial expansion of x minus 1 to the power 2. Okay? So I can formulate x squared minus 2x plus 1 as x minus 1 over 2, but there is an additional minus 1 term here. And with the minus sign in front of the ratio, it becomes a plus. So I also have e to the power 1 over 2 as a multiplier. But that e to the power 1 over 2 is a constant term for this integral, which can get out of the integral simply. And the rest of the integral is in this form. Okay? So this is the rest of the integral when I take e to the power 1 over 2 outside. Now, this integral solution is supposed to be equal to 1. Why? Why it is supposed to be equal to 1? Now, check that out. In the question, I have especially defined the probability density function of a normal random variable. And the probability density function of a normal random variable has the scale parameter here, and the location parameter here. Now, check that out. If the location parameter is equal to 1, and the scale parameter is also equal to 1, so if both parameters are equal to 1, in that case, that probability density function will become just like this, right? So here the location parameter is 1, and the scale parameter is equal to 1 as well, so we do not see it. And this means that integrand here is the probability density function, of a normal random variable with location parameter 1 and scale parameter equal to 1. So the total area under that probability density function should be equal to 1, because it's a probability density function. And therefore, the result is supposed to be equal to e to the power 1 over 2, which is calculated as 1.6487. Okay?